From the soft glow of a firefly all the way to our blazing sun, light is on this constant, amazing journey. But what is it, really? And what are the rules that it follows as it zips across the universe? Well, let's find out. We're going to follow the path of light itself and see where it takes us. So let's start our story with a kid named Keshav. He's from the city, and he's just mesmerized watching the countryside light up with this magical dance of fireflies. But then, as he's riding home, another light catches his eye, the moon. And that's when a question pops into his head that's going to change how he sees everything. It seems like such a simple question, doesn't it? I mean, the moon is bright, so it must be making its own light. But does it? That's the first mystery we're going to solve together. Okay, to answer Keshav's question, we first need to get a handle on a really basic rule of the universe. What things make light and what things just, well, borrow it. It really just boils down to one key difference. You've got your luminous objects. These are the light makers. Think of the sun or those fireflies Keshav was watching. They generate their own glow. Everything else, and I mean everything, from planets to the book sitting next to you, is non-luminous. They don't make any light at all. And there we have it. Just like that, the mystery is solved. The moon isn't a light bulb in the sky. It's more like a giant, dusty mirror. That beautiful moonlight that Keshav saw, it's just secondhand sunlight, bouncing off the moon's surface and traveling all that way to reach our eyes. Pretty cool, huh? So, we know light is on a journey, but what kind of path does it take? Does it sort of wander and meander, or is it following a really strict route? Let's take a look. It kind of feels obvious, right? That light travels in a straight line. But in science, you can't just go with a feeling. You need proof. So how would you, right now, design a really simple test to prove it? What's so great about this test is just how simple it is. You take a straight pipe, look through it at a candle, and yep, you can see the flame, no problem. But the second you put even a slight bend in that pipe, poof, the flame disappears. It's a perfect little demonstration that light doesn't bend around corners. And this simple test proves a huge principle. Scientists have a fancy name for it, of course, rectilinear propagation. But all that really means is that light is a total rule follower. It travels in a perfectly straight line always until something gets in its way. Which naturally leads us to our next question. What happens when something does get in light's way? Well, it turns out it completely depends on what gets in the way. Some materials, like glass or water, are transparent. Light just zips right through them. Then you have translucent stuff, like tracing paper, which lets some light pass, but it gets all scattered. And finally, you've got opaque objects. Think of a wooden door or a piece of metal. They block the light completely. And that brings us to a really cool idea. A shadow isn't a thing that's being made. It's actually the absence of something. It's a patch of space where the light got blocked on its journey. So those long shadows Keshav saw stretching from the trees, they were just places the sunlight couldn't get to. And of course, being human, what did we do with this simple scientific fact? We turned it into art. For centuries, people have used shadows to create pure magic, telling stories and building these incredible worlds with nothing more than a light source, a screen, and their hands. But just blocking light is only one side of the coin. What happens when an object doesn't just block light, but actually throws it back? Well, that's when things get really interesting. That's reflection. The easiest way to think about it is like throwing a tennis ball against a wall. It hits the surface and bounces right off in a new direction. Light does the exact same thing when it hits something smooth and shiny, and we call that reflection. Now, a simple, flat mirror plays by some very predictable rules. The image you see is always the same size, it's right side up, and it looks like it's the same distance behind the mirror as you are in front of it. But there's one really important little twist, something called lateral inversion. You've seen this word on the road 1,000 times, for sure. But have you ever really looked at how it's written on the front of the vehicle? It's totally backwards. Now, that's not a printing mistake. It's actually a super clever use of physics right out there in the real world. See, because of that lateral inversion, that left-right flip that happens in a mirror, this backwards text on the front of an ambulance looks perfectly normal to a driver looking in their rearview mirror. They can read it instantly. It's a life-saving trick, all thanks to a simple property of light. And this is where science just gets so powerful, right? When we take these simple rules about how the world works and use them to build tools that let us do incredible things. Okay, take the periscope. It's such a simple but absolutely brilliant device. And it works by combining the two big ideas we've just covered, that light travels in a straight line and that mirrors can change its path. By just placing two mirrors at the perfect angle, we can actually make light bend around corners. And this simple idea, well, it lets a submarine see above the waves, it lets a soldier see over a trench without putting themselves in danger, it even lets you see over a crowd at a concert. Before we wrap this up, think about this for a second. The sunlight that's hitting your face right now actually left the sun 8 minutes and 20 seconds ago. I mean, if the sun were to just vanish, we wouldn't even know about it for over 8 minutes. That's the sheer scale of space, measured by the journey of light. So we've seen that light follows a few pretty simple, elegant rules. It travels straight, it casts shadows, it bounces off of mirrors. But that leaves us with one last, kind of deep question. How do these simple laws of physics come together to create the incredibly rich, vibrant, and colorful world we see all around us every single day? Now that is the real magic of light.